All right. Hello, everybody. Our next speaker is Kirill Boychenko, and his session has a very cool name, very on brand for B-Sides this year, Slaying the Dragons, a Security Professional's Guide to Malicious Packages. Reminder, Kirill would love to get questions. If you can submit them through Slido, you got to go to the Slido website and type in BSidesSF, or use bsidessf.org/Q&A. Over to you, Kirill.
Hi, everyone. My name is Kirill Boychenko. I am a senior threat intelligence analyst at Socket, where we protect open source and software supply chain at scale. We're meeting at the movie theater, and this means that you guys have comfortable chairs, which I tried. They are really comfortable, but also I get very bright light, and I cannot see anything. So I will try to understand your responses to something that I'm saying, but I may not see it very clearly. Thank you. So yeah, today's presentation, and thank you very much for your interest in coming to this talk, a security professional's guide to malicious packages. And of course, Slaying the Dragons, since Here Be Dragons is this year's BSides San Francisco theme. I would like to introduce you to a fire-breathing animal. So before you guys get worried, because I would, if I were in your shoes, this presentation will not be about graphic design. There are way more qualified people than me in that domain. So, and you can clearly see from what I did to this picture. But the dragon dog, as you can see, she likes many different things. I think I like them too, all of them except for sitting on a high perch. That's not really something that I do often, but let's get to some shared interests with the dragon dog, which is defending open source. The way that we build our software applications today is that we don't start from zero. We take different building blocks, different pieces. We can think about this as gluing something from necessary parts. And that's the beauty of open source. We don't have to be experts in every single feature for our software application. Here on this slide, you can see an example of a software application somewhere in the center, and then many different dependencies or libraries that are included or that our application depends on. And this image is not an exaggeration. This is something that is very common for open source, for software development today. And that's not a bad thing. That's a good thing. That's why we don't have to be experts in every single thing. We can borrow, we can plug and play, we can build upon. And to mention some numbers, the average application today has a lot of open source in it. From 70 to 90% open source in a software application is a lot. We have over 400 million code repositories on GitHub with over 100 million users on GitHub. And there are massive ecosystems for programming languages. We have open source ecosystems for NPM, for JavaScript and TypeScript. We have PyPI for Python. And just these two ecosystems, they accumulate millions of packages and have billions of downloads. Even smaller ecosystems like Ruby gems will still have millions of downloads, over 170,000 packages in Ruby gems ecosystem. So you can see that this is a big these are big data sets. These are big ecosystems, And the bad guys know that too. They understand that today's building of application is designed in such a way that the bar for publishing a package, a new library at one of the major ecosystems is not very high. It's pretty easy for us to publish a package on those ecosystems. And so the bad guys are trying to infiltrate these major ecosystems with malicious packages. Then meant that we would build custom applications. We would spend weeks or months building our software applications. We would start from scratch, and the value was in this custom and optimized code. Now means that we assemble from multiple different building blocks, and we also use AI driven automation to help us code, to suggest, to provide boilerplate code, and the bad guys know that. They know how we're assembling the applications, and they are trying to use it to their advantage. So this is the bluff, or bottom line up front, for our time together today. These are some of the things that we see at Socket, that our threat research team that I'm part of, something that we see on daily basis. This is not an exhaustive list of different attacking techniques and methodologies. Rather, this is something that we see quite a lot in different malicious campaigns that we identify and track. And I will give you more illustrations and examples and walk you through different examples for each of these. We often see that these techniques and methodologies would be combined. So the bad guys will do X, Y, Z, all of them, some of them. We see code repositories abuse. That's basically when the bad guys are infiltrating ecosystems with malicious packages. We see a lot of typosquatting, which is creating deceptive, similarly named packages that appear benign, but they're actually malicious. And typosquatting is a problem not for just one ecosystem such as NPM. We see it across many different ecosystems. We see it across major ecosystems. We certainly see it in all ecosystems that we protect at Socket. So we will see it in NPM and PyPI. Ruby gems, we'll see it in Go, we'll see it in NuGet. So this is definitely a ubiquitous problem for open source and software supply chains. Obfuscation comes as a red flag, comes a lot in malicious packages that we detect. It does make it hard, it doesn't make it impossible, but it's something that we keep an eye on. Multi-stage malware, we see that a malicious package will have first and second stage payloads, which may prolong the malicious campaign or just be designed in this way to change payloads. We see that the bad guys use automation and AI. We'll provide you with some examples of that. And then legitimate tools and services. Not a shocker there, but of course the bad guys, the threat actors, will use legitimate tools and services that we use for ethical research, but the bad guys will use it for things like gaining initial foothold, things like establishing persistence, and for things like exfiltration. Let's start from example of the Go ecosystem. And this example, something that we discovered this year, is was based on code repository abuse. So the bad guy found a way how to abuse mechanism within the Go module mirror. And the Go module mirror is the standard for how to consume and how to distribute and how to proxy Go ecosystem modules, Go ecosystem packages. What the bad guy did is they, back in 2021, they published a GitHub repository and they cloned a widely used module called BoldDB. They made a clone of that. They typosquatted it. They just added a few letters to the name. And at that point, the Go module mirror that is taking GitHub repositories and caches them, especially those that belong to the Go ecosystem. At that point, the Go module mirror cached that malicious package. Later, the bad guy changed their code in the GitHub repo, so it was no longer malicious. They pointed it to the legitimate version of BoldDB, so the repository looked clean. If you were to manually inspect the repository, you wouldn't find any problems. But the Go module mirror already cached the malicious version. So if you were to pull directly from the official Go module mirror, you would be pulling that malicious version. So here we saw a number of things that the bad guy did. You know, they abused this caching mechanism of the Go module mirror, and this mechanism, something that we need to remember, this is built for convenience. It's built for efficiency. The bad guy found a way how to leverage this for their nefarious reasons and purposes, but the Go module mirror and the caching mechanism is actually designed this way to be helpful for us. But the bad guy found a way to circumvent this. And yes, they did typosquatting. They found a module that was very popular. Also, the legitimate BoldDB module was archived. And we as developers, when we would like to pull a module, a dependency, a library, we often would go for something that is not archived, but looks like actively maintained. So that would also be potentially confusing to developers who would look to install BoldDB package. And others may just be confused because of the lookalike names of packages. Also, this package used a obfuscation method that is interesting, but it's not that complex. So BoldDB malicious package had dozens of files in it, and a number of files, 2 different files. They were designed to work together, interact, so to speak, to assemble a backdoor that was included there by the threat actor. One file was called db.go, and it was designed to initiate the backdoor transmission and communication process for this backdoor. Another file called cursor.go had some random looking numbers in it. You can see at the top just some numbers, but then there was a programmatically included logic to transform certain things. For example, 5s would become dots, and 6s and 7s would be completely removed, and so we would get an IP address with a port number, which was that C2 for the backdoor that the threat actor embedded in the malicious package. So not anything earth-shattering, but it did help obfuscate this package and bypass certain detections by the Go module mirror and potentially by some signature-based scanners. Here's another example of typosquatting. This is from another malicious campaign that we identified. Here you can see package named Hyperd, and go, pun intended, figure which hypert is the one that you actually like. You've got to ask yourself a question. Do you feel lucky? Which one is the one that you actually want? Like, they look so similar. I added some, this is not about graphic design, guys, right? But I added a little bit here. So one of them is legitimate, the others are not, but they look so similar. It's this is not that easy. It's easy to mistype. It's easy to get a module that will not be not only not helpful, but will actually be malicious. Here's another example. This one is from NPM ecosystem. So last year, towards the end of October, right for the time for Halloween, our AI scanner detected a large number of NPM packages being published just in rapid fire succession, and we found that the packages were malicious. There was an interesting twist to it. The command and control C2 mechanism that was designed for these malicious packages relied on Ethereum smart contracts, and that allowed the threat actor to have this like decentralized nature of their C2 mechanism, and also ability to change their payload. It added resiliency to their C2 mechanism. And we as security professionals, we know how to block suspicious IPs and domains. That's something that we're well equipped to do. But with this decentralized C2, it was quite difficult to see that there is a C2 mechanism that's included. Also, this malicious campaign, it targeted multiple operating systems, Windows, Linux, and Mac OS. And as we were looking into this malicious campaign, we were able to find the malicious actor. We found the threat actor who was behind this campaign. They did a number of things, going back to that bluff bottom line up front on different attacking methodologies and techniques. They did typosquatting. They relied on post-install scripts, and those run automatically after package is installed in the NPM ecosystem. Especially that's the case. They also used automation for a number of things. They use automation for obfuscating their packages, and they had many packages. They also used automation to mass publish packages to NPM ecosystem. When we found there were already dozens of packages coming in, and then about 280 of them within a very short time period. The threat actor that we found, the reason why we found them is because they were advertising their techniques on the underground dark web forum. They created videos on how they did that. They wrote some articles, they made some posts, and they were very excited on what they achieved with infiltrating the NPM ecosystem. They provided this screenshot. On the left here, you can see it's a screenshot from ChatGPT. They, instead of doing something on their own, they were recommending, just create typo variants of most popular packages using ChatGPT. You provide it with Express, one of the widely used NPM packages, and then just give me typosquatted versions of it. And so they created a long list of typo variants like this, and then they registered some packages with those names that were not yet taken. And you can see on the right-hand side some legitimate packages, most of them related to crypto theme, and then typosquatted versions, right? Just like you can see there's a letter missing or added here and there, and this may seem like not the highest sophistication, but it works. It works in NPM, it works in other ecosystems. It just works a lot. Typosquatting is such a ubiquitous problem. We also found that authors get typosquatted. That was just a hypothesis for us. So I created a script that would pull prolific maintainers on NPM and their names, and then creating typosquatted versions of their names. And there were some hits that we found from that exercise, and the one that you're looking at was most interesting. So prolific NPM maintainer Cinder Soros, the legitimate one is to the left and the malicious to the right. Will the real Cinder Soros please stand up? The problem that we're going to have here is that the impersonator, they included an info stealer in a package that they published, and you can see that the threat actor used very similar profile design, the same picture, and even the package that they published that they called Chalk Node is typosquatting a very popular package called Chalk for terminal coloring. And you can see the legitimate package Chalk to the left, and you can see the file explorer with the directory and files beneath, and then to the right you can see Chalk Node malicious package with a few more files there. And one of the files, specifically index.esm.js, it had info stealer functionality, accessing files on victim system and exfiltrating them. Sensitive information, so pretty classic info stealer functionality. Here's another campaign that we identified and track, and it's also on NPM ecosystem. This is an example of multi-stage payload that I wanted to show you. We constantly identify North Korean attackers infiltrating NPM ecosystem. They are doing this as part of their contagious interview operation. They're trying to infect developers under pretense of testing, debugging, or interviewing candidates or developers for various job vacancies. And here, the multi-stage payload consisted of a number of different payloads. There was obfuscation. The threat actors also used automation for obfuscation in this case. And here's the first payload, which was info stealer and malware loader. And what it did is it was stealing sensitive information from browser storage, some popular browsers like Chrome, Brave, Firefox. It was also stealing Solana wallet credentials. And I should say that we see theft of crypto assets as a common thread. There is a lot of targeting of crypto assets that we find in malicious campaigns in various ecosystems, not just NPM. Then it also had logic to steal macOS keychain credentials. And for the second stage, it would download the invisible ferret backdoor. So it would start from doing all this bad stuff as an info stealer on the infected system, but then it would just add more bad stuff, this additional backdoor. And the backdoor would be installed for persistence and for additional malicious activities. Here you can see the URL in the deobfuscated code, and it would rename itself and unarchive itself and do a few things to also make detections more complex, like that renaming. And it was obfuscated. You're looking at deobfuscated code and code with some comments here. As for obfuscation, the bad guys used a very popular JavaScript obfuscator tool. On the left-hand side, you can see obfuscated. It's a long line of obfuscated JavaScript. That's what it is. It's just one very long line. And there's nothing good about this line. You're looking at it like this line is not gonna do anything good in my system. And then on the right-hand side, you can see a deobfuscated code with some of the code that you've seen from previous slides on the same from the same malicious campaign. The bad guys will use it one-off. They can use it as part of automated obfuscation. We also know that there are multiple free deobfuscators for this very obfuscator, and some of them are online. You're looking at one right now. So it seems like an easy thing to do for the bad guys, but it works. It works to bypass more basic signature-based scanners, and obfuscation is a common theme that we see in malicious campaigns. Also, this example is from NPM ecosystem, and I wanted to show this to you today because it relies on legitimate services, and in this case, the bad guy used Gmail for exfiltration. The target was Solana private keys to drain user wallets. You can see some search results for the two packages. On the top, you can see async mutex is a legitimate package. And on the bottom, you see async mutex that is a malicious package from this campaign that used Gmail for exfiltration purposes. And you can see the number of downloads, which sometimes can be helpful, and I'll explain why sometimes. Here we can see that the legitimate package async mutex on top, it has 1 million weekly downloads and total 93 million downloads. And then on the bottom, we see malicious async mutex that at the time when I made the screenshot, there were zero weekly downloads, but overall only 240 downloads. So downloads can tell us if the package is in heavy use or not. But this won't always tell us whether a package is legitimate or not. The reason is because download counts can be inflated in NPM. We've seen those cases, but this is one of the warning signals for us as threat hunters, as developers, to understand, what's the history of this package. What's the versioning of this package? Why the sudden spike? Can it be explained? Why all of a sudden there are many downloads for this package? We know that the bad guys can inflate those numbers, so they should be taken with a grain of salt. Then we try to, we just Googled. We Googled malicious async mutex package, and we got results from Google AI overview, and the results were not helpful at all. It just gave the stamp of approval that this package is safe, that we can install it, but the package is malicious and shouldn't be installed. The problem with AI-generated results like this is because LLMs sometimes tend to be overconfident and sometimes tend to be overeager to help us with what we're asking. And here, Google's AI overview is trying to be helpful, pulling information about this package from README of a legitimate package, but we're asking about this malicious one, and we get a result on how to install it and information from the legitimate one. So not not helpful at all. And this goes back to the beginning of my presentation on AI and the use of AI, and we will come to this again. So back to this Gmail exfiltration. So the way the bad guy did this is they hard-coded Gmail accounts and Gmail addresses for exfiltration mechanism, but they also hard-coded the password. That was really strange. You just don't see this a lot in libraries. Like, why would someone hard-code their email address and their password? Well, yeah, for this reason, to exfiltrate sensitive information from infected systems. In a similar attack, the threat actors went one step further, and they, in addition to providing their Gmail addresses and hard-coded password, they were also draining 98% of the funds. They would leave 2% likely for transaction fees, but they would use Gmail for exfiltration, and that they would also transfer funds to a provided Solana wallet address. This example I wanted to show you because this is yet from another ecosystem, and this is from the Java ecosystem and the Maven central repository. So the bad guy here, they cloned a widely used package called XC for Java. After cloning that package, they included a backdoor code in it. They also used AI and automation to generate malicious code and their malicious script. And they also did a few things that we see a lot. First, publishing benign version, and then in a later iteration, later release, including malicious functionality. Here's the code. All the code that you've seen in this presentation before, all the comments, those are mine, but these are not mine. These are threat actors. I believe not even their comments. It's more likely AI generated code, AI generated obfuscation that the threat actor used to help them generate this malicious code, obfuscated basic array byte obfuscation, but again works for some to bypass some basic scanners. And they yeah, of course, there's 1337 for leet. Well, almost too many digits, I think, but it has to be bad if it's leet 1337, I guess. And very helpful comments, very AI-like suggestions to this code. Another example from Python package index, or PyPI. And here the threat actor typosquatted widely used browser cookie 3 package. They just added letter S. And what's interesting about this package is they included an unexplained binary called client.exe. And so we decompiled their code and came back to the original Python code and found some modules that it would use, and it would screenshot victim system victim screen. It would steal passwords. It would access user camera, and then it would exfiltrate sensitive data to a Discord webhook. We see the bad guys are using things that we can also use legitimately, right? Like a Sentry instance used for error tracking, but will be used for exfiltration. Discord webhook would be used for exfiltration in this case. So this is, or Gmail in that other example, because perhaps, well, SMTP traffic may be totally normal for that environment. And this is an example from Ruby gems. and once again about threat actors using legitimate services and tools. We find that threat actors will use out-of-band application security testing, or OST, something that we use for security research and for testing purposes. Threat actors will use for things like exfiltration, or as in case with this malicious campaign, they use it as initial reconnaissance. And as an initial recon tool, they use it to profile victims. They got information about the system, about the user. They would exfiltrate it to OWASP-related domain, ostify.com, to later position their attack better, which could be, for pivot, to understand privilege level, to understand the environment that installed this package. So we're circling back to where we started. I gave you some examples of threat hunting opportunities, but things to look out for, and we do in our work, which is scripts that will run automatically, like post-install scripts in NPM. Obfuscation, does it always mean that we're dealing with a malicious package? No, it doesn't, but it may be a signal for us, and the more signals, the merrier. Hard-coded network calls, some unexplained stuff going to endpoints that shouldn't be going, should raise some alarm bells. Dropping executables as not unexplained, not described in any way, something that later can infect the system. We see those packages too. And for defenses, the list can be very, very long. I didn't want to overwhelm you, but certain things that we need to know is that we are already at that point in time when developing our applications and relying on external libraries, which is a good thing. Open source, that's why open source is such a wonderful thing, and that's why we want to protect it, is because we can build and share and build upon on work that has been done, and include certain features. We don't have to reinvent the bicycle. But there is no way that we can vet all of those dependencies and libraries manually. There's just too many of them, and there's a lot that may be happening inside that code. So we need to be able to scan the code. We need to be able to vet it. We need to be able to approve it. We should have an allow list for our critical infrastructure. We should have an allow list for production apps. We should be able to restrict packages that deemed malicious. And with that, I would like to thank you for your interest and for attending today's session. Since I think this session is being recorded, I also want to thank my team at Socket. I want to thank Kush, Olivia. I want to thank Sarah, especially Philip and Feroz, but most importantly, thanks to you guys for coming to this talk today. I appreciate it.
Thanks, Kirill. A couple of questions for you. So first one, since malicious packages don't have a CVE standardization, how are you unifying your malicious package research with the broader community?
Yeah, that's a really good question. So and I should have said that all the packages that I presented to you today, all of the malicious packages, we report them to the respective package registries, because we believe that, after we analyze them and as we publish our findings, we should be able to also work with package registries so they can analyze malicious packages too, and they can block them and stop them. And we believe that collectively we can stop the compromise. So we're sharing with the community. Also, you can see the way we standardize hunting for malicious behavior. It's open information. It's on our website. We have more than 70 indicators how we verdict and determine that there are certain malicious indicators or signals in packages. And we have also a number of free tools that any developer can use, and it's very easy to install, just a few clicks, and the information is there. We were pretty open about it.
Another question for you. How prevalent are these malicious threats? Why don't package managers do more to prevent these malicious campaigns?
Excellent question. I think that this is from one hand, you want to encourage innovation and keep open source open, so we can take advantage of all those wonderful tools that different developers build. And package registries, my understanding, are trying to encourage this innovation and open source nature of this work. At the same time, those are massive data sets. Like we were talking about at the beginning of the presentation, we have like millions of packages in a given ecosystem and billions of downloads, and then there are updates and new versions. This is not a trivial task, and we know that security teams at various ecosystems, they're doing their best. It may not be good enough for us. We certainly need to trust code that we allow into our systems. So they're doing some work. It's not good enough. We're trying better from our perspective. Yeah.
Why doesn't NPM do more to address abuse of their platform? Fake download stats, ability to claim namespaces without validation, trusting metadata from package.json for author and collaborators. These are all things that NPM could fix.
I agree with you. The answer would be, I don't know why.
Somebody else said they do, it's just slow.
Okay. Perhaps that's a good response. I should take it for when I have a question like this. Yeah, I don't know why. I'm not with Node.js, and I'm not from NPM security team, but I agree with your sentiment.
Is dependency confusion still a concern?
Yes, it is. We found that Black Busta ransomware gang was actively testing this theory of dependency confusion, is finding package names for that companies use internally, and then publishing something to public registry in hopes that at some point the tooling of that company will go and fetch that package from the ecosystem, and there will be bad code in it, malicious stuff. Yeah, still a thing.
Final one for you, Kirill. How well does the takedown process for known malicious packages go?
We have very good feedback from PyPI and their security team. Whenever we publish our research prior to the publication, when we do our research and discovery, we send takedown requests to PyPI, and they respond very, very promptly, very professionally. The same goes to Go Module Mirror. As for NPM, they take time. Probably that's to the point of one of the people who asked the question. They do it, but they do it slow. We see those packages get suspended, but it's not as fast as we would like to see it.
Awesome. That's it. Thank you so much, Kirill.
Thank you.